All right, so let's have a look at some of this stuff. That's just weird. All right, so what we are looking at first is this Instantaneous Center stuff. So we have 301. All right, now 301, what's going on is this wheel is rolling. Now, one thing you want to keep in mind for this particular one is what the characteristics are of the instantaneous center of zero velocity and how you go about finding it, how you identify it. All right, and the basic ways that you identify it are that you identify velocity vectors on the object, okay, and use perpendicular lines that run through the velocity vectors at the point where they're applied, and then intersect them at the instantaneous center. That's the basic visualization we want to do there. The other thing about the instantaneous center is at that instant, it doesn't move. All right, it's motionless at that instant. Now, the funny thing about instantaneous center is it moves all the time too, okay? You know, every instant you look at the object, the instantaneous center is in a different location. But for the instant you analyze it, it's the point that has zero velocity. And it's found by finding a perpendicular to a velocity vector, and that would run through the instantaneous center. It's as though the whole object at that moment is rotating about the instantaneous center. So sometimes I think about it as being a pin joint, and my object is being somehow attached to that, just at that instant and rotating about it. Okay, so that's how I visualize this thing. So when you look at this first one here, what we have is this wheel that rolls without slipping, and that's the key thing. See, what's happening here is this point E on a wheel has a zero velocity, doesn't it? Okay, so what you can visualize there for just that instant is that's the instantaneous center, because it has a zero velocity, and you can think of that wheel as rotating about that point as though it's a pin joint just at that instant. Okay, so what you want to do then is figure out what the velocity of the wheel is. It's omega r, and we got omega, and we got the radius of the wheel is 0.5. Okay, so if you multiply those together, you get 2 meters per second. So what's happening is the velocity of the center is 2 meters per second. Okay, so that's what's going on. Now also omega is omega. I mean, so omega is 4 radians per second, regardless of how you find it. If you have omega, you found it for all methods. There is one omega for the object that holds for relative velocity and the instantaneous center method. So what we're seeing here is this distance here is 0.5 meters. And so what we've got then is the velocity of c is omega r. And see, that stuff all fits together now, doesn't it? Because we've got 2 meters per second for the velocity of c. We've got omega is 4 radians per second. And we've got the position of the center with respect to e. Okay, what that is 0.5 meters, see? And see, that all fits together, see? So what we get out of that is that entire wheel can be thought of as rotating at 4 radians per second about point E. That's how you can think about this. So if you can find out how far any of those other points are from point E, you can determine their velocity because you know a distance and you know omega. All right. So we good with that? We got any questions on what I'm rattling off about with that?
I was having a little bit of trouble with point H.
H? Okay, yeah, H is probably the trickiest of the bunch. The geometry is a little bit tricky. Okay, so your goal now, once you know omega, is to find those distances. That's really what you want to do. All right. So, all right, now to find H, it's a compound kind of thing. That's 0.5 meters, so's that. So what you got to do there is use a little bit of trigonometry and get that last little bit from C to H worked out. Okay, so from C to H, what we've got is a right triangle like that. And so what do we got going on here? That's 60, so that leaves 30 in our triangle. All right, because this is 60, and it's a right angle, so that's 30, and this is 0.5. So what you're going to do then is do the trig, and you're going to get 0.25 and 0.433. It's cosine 30 times 0.5, and 0.25 is sine of 30 times 0.5. So sine is the opposite angle, opposite side. Cosine is the adjacent side. So if you take that information and kind of put it all together, what you'll have then is you'll have from E to H is a triangle that looks like that. Now you've got 0.5 more, so this is 0.933 and this is 0.25 here. See, what we've got is an extra 0.5 down there to get from E up to C. So if I kind of make a little diagram out of that, that's E, that's C, oops, not E, that's C. I'm out of scale here. And then that's H. You all with me there? So what you can do then is you can just make that into a triangle, just cut straight across like so, and that's how you can get the distance. So what you've got then again is you've got 0.933, which is the sum of 0.5 and 0.433, and 0.25. And then you're just going to cut the hypotenuse across. So you can get that distance, and we call them radii, even though they're not. It's just the variable that they seem to use for this. And this is H with respect to E. And of course, it's just theorem of Pythagoras there. So 0.933 squared plus 0.25 squared. Take a square root, and then you get that distance, and that's 0.966 meters. Okay. You all good with that? And so then if you want to find the velocity of point H, what you're going to do is go omega r, and that's 0.966 meters. Whoops, that's r. So I'll put omega in there first. Omega is 4 radians per second. And then r is 0.966 meters. And so that'll get you the velocity of H, and that is 3.86 meters per second. Okay, so what H is doing, it's not tangent to the circle actually. It's kind of splitting the difference. It's going off that way. I think it's like 15 degrees down below the horizontal there. It's kind of doing that. Okay, and that's 3.86 meters per second for VH. And then if you find any of those other distances which you'd want to do to do the rest of this problem, what you'd want to do then is to get this distance and then that distance to get the rest of that figured out. Okay. Okay. We okay with that? Okay. So that's the approach on that one. The key fact, and this is something to kind of, especially if you're a mechanical engineer, because you'll be doing more of this stuff. Kind of put this one back in the file somewhere that you can analyze wheels that way if they roll without slipping. They're just like they're hinged at the bottom for that one instant. Okay, just for the instant you're analyzing it, you can do it that way if you want. Okay. So we got any other questions on that? Okay. All right, so that's that one. Now the next one is a linkage problem, and it's one that we've done before a few times here, so we'll do it again. All right, so now keep in mind that this homework, I want you to use the Instantaneous Center method on it because I want you to learn it that way. But again, I've been harping on this, and I'll say it again. On the exam, I'll probably get you one of these linkage problems, and you can do it any way you like. Okay, so just find the way you like and get it dialed in. But on this homework, use the Instantaneous Center method. Okay. All right. So what's going on here is you start just like with the relative velocity approach. You start with what you know, and what you know is A isn't moving, and that you've got omega here at 1.7 radians per second. And then you've got 0.42 meters for the radius there. So that's A over here, and here's B. So what A is the instantaneous center for AB, okay? So A is the, and I just use IC for instantaneous center or zero velocity. For AB, okay? It's only the instantaneous center for AB. It's not the instantaneous center for BC, so remember that, okay? And so what's going on is B is rotating about A, and it's not quite on that line of BC because that's not a right angle, but it's close. But it's not on that line, but it's doing that. Okay, so what you want to do is find the velocity of B, okay? So to find VB, and it does look like I've got this mislabeled, that should say VB there, is 1.7, which is the angular speed, times the 0.42 meters. And what that is 0.714 meters per second. And that's going down like that. Now what's going on here is we've got the linkage itself makes a 28-degree angle there. We're perpendicular to that, so that's a right angle. By parallel angles, we've got 28 degrees there, so 90 minus 28 gets you 62. So that velocity is going down left at 62 degrees, and that's VB. Okay. So we good with that? Any questions on that bit? Okay. All right. Yeah. Uh-huh.
So I did the instantaneous center, and the three angles,
Mm-hmm.
one of them was 62 degrees.
Yeah.
Were you supposed to like pull that away from the other 62 degrees? Because I had to find it a different way. But it still ended up being 62. You get 62 on the top.
It's 62 on the top, yeah, and
Is that just coincidence? Or?
no, it's not coincidence. There is a relationship there. And I know, it's funny, I've been doing this for years, and I don't have like a standard way of finding these things. I find them a different way every time. So there's lots of ways to find the angles. So the one thing with geometry, and like I say, I'm a civil engineer and I've done surveying and stuff, is just prove it to yourself. The one problem people have is when they start doing intuitive geometry, they start pulling these angles out of the sky, and that doesn't work. But I draw pictures and I prove it. Going back to what I did in high school with those proofs and all that stuff. I mean, that's how I think about doing this stuff. So if you can prove it, it's probably good. And I think you can prove that 62 because you got a right angle, and that's 28, and 60 minus 28 gets you to 62 right there. And that's how I did it. Now, there might be other ways to do it too,
Because I found the 41 and the 77.
Oh, and subtracted?
Subtracted from 180
Yeah,
to
sure.
62 and was like,
yeah,
really?
It all checks out. Yeah, and like I said, there's more than one way to do it. There always is on these things, okay? All right. Yeah, so, and that's kind of the next task here is to kind of get this stuff, get these angles. Okay, you're given 49 here, so 90 minus 49 is 41. Okay. And the one I always kind of do differently is this one. There's two ways to do it. You got a triangle 180 degrees. You can take away the 62 and the 41, and that'll get you, whatever the heck that is. Is that 57? 67? 77, okay, 77 degrees. So there's a couple ways to do it. One way is that. So you can just take the 180 for the triangle, and you've already found the 41, and you've already got the 62. So that leaves 77. And the other way to do it is to use the parallel angles to the 28 and the 49. And this is getting to be a bit of a mess, I'm sorry here, but this would be 28 right here by parallel angles. And this other one will be the 49, same argument there. That's a little theorem. That's one of Euclid's theorems, right? Those parallel angle things. Okay. And that's 49. So if you take 28 and 49, you get the same thing. You get 77. Okay. So, different ways to do it. But it's kind of good when you do it two different ways. You get the same answer. I mean, that's a good thing. You got to check. Okay. So what we got now is we've got a triangle there. And what that's doing is that's kind of defining this relationship. And now this triangle only holds for BC, all right? So, I've got that going on. That linkage, I'm drawing straight up from here. Now, what I'm doing here is I'm drawing perpendiculars to the velocity vectors. All right, so this velocity of B is, by definition, it's perpendicular to AB, right? So that means if you draw a perpendicular through that point B, perpendicular to the velocity vector, that's running right up AB, okay? It's always that way, okay? Now the other thing is we've got BC, and what C's doing is it's running on this rod like that. Drawing a perpendicular to that, it's going to go straight up, okay? That's why that's straight up, because the actual velocity of C is horizontal, so the perpendicular to it is vertical. Okay, now the important thing here on this to remember is the IC for BC is not equal to A, okay? A is the IC for AB, but it's not the instantaneous center for BC. The instantaneous center for BC is on the linkage AB, but generally speaking, it's not point A. Unless there's some odd coincidence going on, it's not going to be point A, all right? Because BC is, AB rotates about point A, but BC does not, okay? Generally speaking, all right? So the goal then is to find this triangle right here, because that includes the linkage that you're dealing with there, BC, okay? And that's what we're doing with those angles. We're trying to define that triangle, okay? All right, and so there it is, okay? So I've got this vertical line, and then I've got the line that goes from A towards B, and there's my instantaneous center. And then I've got 41 here, I got 62 and 77. And the three of those add up to be 180, which for a triangle, that should happen. So 62 in the vertex, 41 down there by C, and 77 over by B. Okay. We also know the length of one of these sides. Okay. So if that's the case now, we can figure out that triangle. Because what we've just found out is this thing is rotating about the instantaneous center. We just figured out where the instantaneous center is. It's up here. We know that this is 0.3, and we've also got all the angles on this triangle, which is a good thing because now we can use the law of sines and get this triangle figured out, okay? And we know that VC is doing that because this whole thing is coming around clockwise. So VC is going to the left, okay? Because the whole thing's rotating counterclockwise about the instantaneous center right now. So again, if it helps to visualize, put a pin joint up there. The whole thing's just swinging clockwise. Now we need the distances is what we need. And we're fine with that because what we know is from the law of sines, if we take that 0.3 and divide it by the sine of the opposite angle, that gets us a ratio that we can use to the sine of the other angles. So sine of 41, sine of 77, sine of 41 is opposite B to the IC, and sine of 77 is opposite C to the IC. So I can create those ratios. Okay. Yeah, a question there? No, okay. Now on the back, I've got the law of sines. That's what I'm doing here. It's a trig identity or something like that. And I put it in its normal sense. Normally they got the sine over the distance. But if the sine over the distance holds for those three ratios, so will the distance over the sine. It's just the inverse. And I like to use the inverse because that way the variables are on top. And algebraically, it's just easier to solve for them. That's why I invert it. Okay, it's just the algebra is a little quicker. Okay. All right. So I've got one of those, it's all numbers, so I can solve for that number. And then once I've got that, I can solve for the others. So I can get all the distances. So B to the IC is 0.2229 meters. And C to the IC is 0.3311 meters, okay? So I can get all those distances. All right, so this is 0.3311 here. And then this other one here is 0.2229. All right, so once I've got there, what I got to do first is find omega. If we're okay with that, and see, I can do that because I know what the velocity of B is. I already found it. it's 0.714. So what I can do then is I can just I use these relationships. So V is omega R, omega is V over R. And so I've got the 0.714 meters per second, and I know what the moment, or I call it a moment arm because it's really kind of what it is, the radius, I guess the 0.2229, and I can go ahead and solve for that, and that comes out to be 3.20. So at this instant, linkage BC is rotating clockwise at 3.20 radians per second about the instantaneous center. That's what it's doing right now. And if I know that, I can find V equals omega R, because now I know what omega is. At this instant, the whole thing's rotating at 3.20 radians per second, and point C is 0.3311 meters from the instantaneous center. And I can just run that and get the velocity. It's 1.06. All right. We're good with that. So that's that method and how that goes. Now this method's probably the strangest of the bunch, really, of the three. It kind of, it's a little bit out there with some of the geometry, at least in my way of thinking. I think it is the fastest method, though, if you're comfortable with it. You just kind of bang, bang, knock it out. If you got to be able to do the geometry. That's the little thing on this, is you got to be comfortable looking at those triangles and getting the angles figured out. And then you actually got to believe the lost signs on the back. I guess I've had trouble with that sometimes with engineering equations. Like, I'm building this spillway, and I'm like, does this equation really work? Can I trust this? Like, even though it's in the book and it's all been said, it works and all that. But all the same, sometimes I have this moment where I think, can I really trust this? Okay, so we good with that?
With these collar linkage problems, you don't have one of those videos that shows the motion of what we're looking at, do you? Because it's sort of like the diagram isn't really. It's just not accurate technically. If it's actually doing a full rotation.
Well, they're not doing a full rotate. Well, it depends on how they're put together. Normally, the ones I draw up, you're right, they can't do a full rotation.
Right.
It's going to lock up.
To a certain point.
Yeah. And someone was pointing that out to me. I can't remember. Someone was asking me about that. And yeah, you're right. They can't go. It's not like an internal combustion engine where it can go all the way around.
Yeah.
It's the first linkage is too long, and it can't do it. You're right.
And that's fine. Just I guess it's like so. I need to understand that somehow something that stops.
Yeah, maybe it would reverse or do something like that. Yeah, I mean, if you look at an internal combustion engine, you just got a little bit of a lobe there, and it's kind of offset, so it can go around. But yeah, ours.
But the idea is that it's sort of a piston, it's going back and forth.
Yeah.
Some sort of like fluids and any sort of motion.
Yeah, so I would think of it as reciprocating, maybe back and forth. Yeah, this can't make a full circle.
Okay.
All right. Okay, we're about out of time. I did want to cover this stuff. Now, a couple of things. We'll cover we'll do the acceleration tomorrow. If you want to turn this stuff in up to Friday, I don't really care. I'll put a key up, okay? Because we got a little behind because of the snow and me being late today. You can turn it up through Friday, and I'll have a key up so you can look it over. I mean, I like you to have it in your hands the night before the test so you can look it over. So you can do whatever suits you, okay? Whatever works for you. If you turn it in today or tomorrow, I'll get it back to you.
When will you have it graded? It's due Friday.
This homework, I'll grade it the day after you turn it in. So if you turn it in today, I'll get it to you tomorrow. If you turn it in tomorrow, I'll get it back to you Thursday.